As you are already aware, it is very simple to create multiple variables in your code. Here we have three integers, x, y, and z, each set to an individual value. As they stand right now, they are completely separate values. They don't interact with each other in any way, shape, or form. If we wish to pass these values to another method, which I'll create here, I'll call it static void test method, I would have to create three parameters that would accept these values. So to call test method, I would have to say test method and pass it x, y, and z, as they are independent values. Then I could do something silly like just print the result of adding all three of them together in the method. What the method does is not the important part of this demonstration. The fact is, if I have to pass these three variables to a method, they have to be passed independently. Not so much of a problem when it's only three values, but what happens when this increases to something like 20 or 40 or 100? Then, as you can see, the test method would get ridiculously large, at least as far as its parameter list is concerned. One of the ways to get around this problem is to group these integers together into a single entity known as an array. An array is a data structure that contains like elements. Physically, in memory, an array contains one contiguous block of that memory. So if I were to create an array of 10 elements, all of those 10 elements would be back to back, starting from a single memory location. That is not particularly necessary to know in C# because most of the time we are not going to be doing direct memory accessing of an array where you possibly would do that in C or C++. Instead, we would access array elements by an index, which simply says return or set a value at a given location in the array, and C# will determine where that is in memory, so you don't have to worry about that. So let's create an array that will contain these three elements. There are actually several ways we can declare and initialize an array. The first is the longhand syntax, where you will declare a data type with the one-dimensional array index specifier here, this set of square brackets. Then you'd provide an array name. We can just call it A. We set it equal to a new, and what comes after the new is the same thing that was before the variable name declaration, except within the square brackets, as you can see, there is a red underline. We have to specify how many elements we wish to store within this array. Since we are going to put 3 elements in there, we will specify a 3 at this location. As I mentioned, this is known as the longhand syntax for creating an array. There are actually shorter versions that are probably a little easier to read as well, especially if you're going to initialize the array at the same time as you declare it. Let's just assume this is how we are going to work with the array for right now. How would we get the values x, y, and z into the array? To access an array, you'll specify the name of the array. In this case, it's A. Then using the square brackets, this is known as the index operator or the indexer. We have to specify which element we wish to assign to. It's very important to remember that in C# all arrays are zero-based unless otherwise specified. And I say otherwise specified because there are mechanisms that you can use to make non-zero based arrays. However, it is not a very common technique and it's not likely something you'll see out in the wild. But they are zero based, so the first element is always going to be at index 0, not index 1. and then I have a choice. I can assign the literal constant 1, 2, 3, or I can specify x. Either way, this is going to do a value copy out of x and into the position at array A, index 0. So in reality, the 1, 2, 3 would execute faster because there is no memory lookup for x, but the end result will be the same. It'll be the value 1, 2, 3 stored at array index 0. The next value, as you could probably guess, is going to be A with an index of 1, and I'll assign that equal to y, and then I will finish this off by assigning array index 2 equal to z. This is another curious result of the fact that arrays are zero-based, is that the last valid index is always going to be one less than the number of elements. Since we have defined an array of 3 elements, A with an index of 2 is going to specify the very last element. If I were to try to assign something to an index that is not within range as such, let me just put a breakpoint on this line, and we'll run the code. As you can see, we sailed right through setting A 0, 1, and 2, and if I bring up the watch window here, I can add A to my watch list, expand it, and you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. But notice there is no 3 index here. So this assignment is going to go to a location that's not valid. If I hit F10, you will see that exception, which is an index out of range exception, thrown. This is one of the nice features about C# and .NET in general, in that if you try to access an array out of its legal boundaries, you will get an exception. In other languages, namely C and C++, you are perfectly allowed to write values at any address you wish. Most of the time it's going to cause your program to crash with an access violation, but the fact of the matter is, accessing an array in other languages sometimes allows you to go beyond the valid limits. So index -1, as you can see here, this is not even going to be allowed. Again, C# is in charge here, and it's making sure that we cannot do something that is potentially damaging to the system. When I say damaging to the system, I don't mean physically, but I do mean causing instabilities in your program. As a matter of fact, there are many vulnerabilities that Microsoft still continues to fix in old programs that are part of the Windows operating system that are susceptible to these problems where you're writing data outside the bounds of an array and therefore allowing some malicious code to sometimes execute. Because of our declaration here, where we specify this is an array of integers, that is the only thing that can be placed within the array. I'll remove this last line since it's invalid anyway, and I will try to put a value that's not an int inside this array. See, now the problem is it says this is a double precision floating point number, and we can't implicitly convert from a double to an int. So just like with accessing elements outside the bounds of the array, we are also not allowed to assign types that are not valid for that array. So in this case, everything has to be an int. Theoretically, you could create an array where the base type here is object, and then you can fix the rest of the declaration and initialization as well. And yes, then you can put anything you want inside of this array. The downside is now we're not being very type safe. Basically, you're throwing caution to the wind because any element could be anything you would like. Also, if I were to put value types in the elements of this object array, I would be doing boxing at every single step. So this is one of those techniques I highly recommend not implementing. Don't create object arrays unless you absolutely have to. There are legitimate instances where you have to use an object array, especially when accessing things like the Microsoft Office interop libraries using .NET. Sometimes you have to pass a list of items, and rather than specify all strings or ints, they allow you to pass objects, and then the Office libraries will figure out how to parse that information. However, in robust coding, we try to be as type safe as possible, so attempt to stick within this style of creating your arrays. Stick to a given type. Well, you know how to assign values to an array. How do we read values out of them? Well, let's go back to test method and change it so instead of accepting 3 integers, we will accept an integer array. And here's a nice little trick that C# provides. Notice here I just passed the array. I don't specify how many values are in the array, plus I don't have to provide a second parameter here that indicates the number of the elements in the array. This is something you would normally do in other C-style languages, because when you pass an array, you're really just passing a pointer, which is a single address location in memory, and the count would specify how many elements are legally part of that array. So we can bypass that in C# and just pass the array as such. Then the question may come up, how do we know how many values are in the array? Well, the good news is, if I were to type A and then dot, you'll see several methods, one of which is length. And that's going to return an integer representing the total number of elements in all the dimensions of the array. Since it's a single dimensional array, I don't have to worry about possibly having 2 dimensions and therefore many more elements. This is going to indicate the total number of elements I have for my one-dimensional array, or I could call get upper bound, passing it dimension 0, the first dimension of my array, and that will also return the number of elements. The difference is when I say length, it's going to return the 3. That's how many elements there are. When I ask for get upper bound, it returns the last legal index, which in this case is a 2. They can be used similarly. They're not completely interchangeable. For purposes of consistency, I do recommend sticking with the get upper bound call, because once you move into 2-dimensional arrays, length is no longer going to give you the length of one dimension in the array. It's going to return the total number of elements. So if you had a 5 by 3 array, that gives you 15 for the total length. It wouldn't give you a 5 or a 3 back. So get upper bound is typically one of your best bets. Now, we can make assumptions that we only have 3 elements passed to this method, but rather than do that, I will introduce a simple loop that will give us the same effect that we had earlier, which is to calculate the sum of the values. And I'll do this in several steps to make it relatively clear. So I'll create a value called sum and initialize it to 0. Then I will create a for loop, which will start at the index 0, and while it's less than, and I'll move this code for get upper bound up here, I++. You may not be familiar with for loops at this point, so let me just walk you through it very quickly. We are saying create a new variable called I and initialize it to 0. Then, while I is still less than get upper bound, augment I by 1. Now there's a couple of things in here that I purposely left as a problem so we could work through it together. So if you're like having little red flags pop up in your head right now, like there's something really wrong with this, don't worry, we will get to them. Okay, first, a lot of people like to do this, the ++i instead of I++, for theoretical speed increases. And yes, in other languages like C and C++, there is a significant difference in speed, especially if you're doing this many, many thousands of times. In C#, that difference isn't as pronounced, but it still exists. Therefore, unless it really bothers you, you might as well go with the quicker syntax of ++i. Now the second thing is, notice here I'm starting at 0, and I'm saying continue to execute the loop while it's less than the get upper bound of index 0, which should return 2 in this case. But the problem is I will never reach 2 using this syntax. That is because we're saying terminate the loop as soon as this statement is no longer true. And that'll happen as soon as I is kicked up to 2 after this per iteration of the loop. So to fix this, I want to say less than or equal to the get upper bound. Now, had I used length, that loop would have looked slightly different. So instead of get upper bound, let's say this was length. Now I have to get rid of the equal sign because length is going to return the total number of elements. I'm going to comment this second one out for the time being, and I'll finish writing the code to calculate sum, which would be sum plus equals a at index I. Then I could output the sum as such. This a at index I, sometimes referred to as a of I, or the element at index I of array A. There are many different ways to say it. It's going to start with I being 0. So sum is initially going to add the value 1, 2, 3 because that is what is at the first index of the array. Then we're going to finish the loop, the first iteration. We come back up to the second iteration, augments I by 1, and then we're going to see what's at A index 1, which is 4, 5, 6. That's added to it. We do the loop one more time, augments I by 1, and then we find out what's at at A index 2, and that is added to sum, and then we get the result. So if we come back up to main, get rid of some extraneous spaces here, all I have to do now is pass A as the value. I don't have to pass X, Y, and Z, and then I can run this code. Well, before I do that, let's put in a read line so the console window doesn't shut prematurely. And here's the value, 1,368. Another nice thing about the way this method is implemented is that because we are not specifying how big the array is, if I were to create another array, and I'll use a different syntax this time, I'll say int array, and then we'll call this array A2 is equal to, and instead of specifying new data type and then size, etc., I can just apply the values I wish to put in here. So that allows me to bypass the assignment phase of this array, which took 3 lines before. Now I've done the declaration and the assignment of the default values into the array all in one line. But I can add, besides X, Y, and Z, I could also add 555. As long as it's an int, it doesn't matter. Now A2 is going to be a 4-element array. I don't have to specify it anywhere. It is going to figure it out based on the number of elements I pass to this list initializer. And then I can call test method again, this time with A2. And if I run the code one more time, you'll see now I have the results from that 4-element array. I didn't have to change anything inside of test method to support the new size of that particular array. Now, one thing you do have to be careful about with arrays is that the array data type in itself is a reference type. Even though I have values in it like ints, you might think, oh great, here's that boxing thing again. You don't have to worry about the boxing with an array. All I'm saying is the array itself is declared just like any other reference type, so you have an allocation in the stack that points to an area of the heap, and the heap is where the data is going to be stored. But the individual elements of the data, the items, they are not going to be boxed. So if I have this set of ints being initialized into my array, the heap is going to allocate, in this case, 16 bytes worth of data, because each int is going to be 4 bytes, and I have 4 of them. So yes, we still have one layer of indirection because we are not accessing the first element of the array directly like you would in other languages, because we have to still step into the stack to get to the address in the heap. But once you have that, it's direct access to all of the data in the heap directly without boxing and unboxing. So here's that problem I was going to bring up before I went on that tangent. If I had int array3, A3, I can assign it a null, and then I can call test method with A3. Did the alarm bells go off yet? They should, because I have a problem here. I'm passing essentially a null into this variable, this parameter A. So when it tries to access this get upper bound, it has no reference to get the upper bound from. So that's why we will get a null reference exception when this runs. So it is a good idea that anytime you accept an array for a parameter type, that you definitely check to see if it's null prior to accessing it. So in this case, I would say if A is not equal to null, then we can perform this code here. Another nice feature about arrays is the ability to utilize the IEnumerable interface methods. Because all arrays are enumerable, I'm not talking about enums, which is a completely different topic. I am referring to the fact that these arrays participate in obeying the IEnumerable contract that specifies there are certain methods that must be there. I'm going to comment out this set of lines here where I call test method with a null object, since we know that's going to end the code prematurely. Knowing A2 is not null, I can say A2 dot, and you'll see all of these methods that are known as extension methods. It's the purple cube with the down arrow. Anytime you see that, those are methods that are not really part of the array, but they're part possibly of some other interface that this array belongs to, and therefore it must implement. And one of those methods, if I get down there, is called sum. So rather than having to write this test method, I could actually extract the sum by using that extension method of the array. If I run this and step over the method, you'll see that sum is 1923. So I basically could bypass this test method altogether. So it's a good idea to get used to some of these extension methods that are built into the IEnumerable interface, and that the array type of arrays of all types must also implement. Some of the other more interesting ones are like the average function. So we could have taken our sum and then divided by the number of elements in the array and come up with the average, but as I mentioned, it's already here, so we can call that directly. And as you can see, we have some methods that are part of the array definition interspersed with the ones defined by some of those external interfaces, the extension methods. because they don't have the little arrow next to the purple cube, such as like get upper bound, which I showed you earlier, get lower bound, which is not that useful since it's always going to return 0. Here's a nice one, last. If you're only interested in the last element of the array, you can ask for it specifically by saying last. And you could also get the first element, which this one isn't as useful because first is always going to be index 0. But if you're only interested in the last element, you can simply just say last, such as int last is equal to a2.last. We also have a min and a max method. They allow us to return the highest and the lowest, not respectively, because I said it in the opposite order. But if we say get, or excuse me, just say max, that'll give us the highest value that's stored in the array, and min will give us the lowest one. By the way, the rank property is going to return the total number of dimensions of the array. So if you pass an array without specifying dimensions to a method, you would be able to retrieve the number of dimensions using that rank property. Then we're going to get into some more advanced LINQ style query methods such as select, where it will allow you to do things like tie it with a where and group bys, so you're almost performing SQL commands against the array. That would be a different topic and a different conversation, but it's also a very useful technique. One of the biggest drawbacks to an array, however, is the fact that they're not dynamic. Dynamic meaning once you've defined the array, you cannot change the number of elements that are in it. This is known as immutable, and just like strings, if we were to attempt to append any additional data to the end of it, we simply can't do it as a single operation. Basically, memory has to be shifted for the new elements to fit, and rather than do that in place, .NET optimizes it so you would have to create a brand new array completely, copy the contents from the source array to the new location, and then insert the new values. As it sounds, it's a fairly expensive proposition. So it is frequently frowned upon to repeatedly redimension an array, in other words, changing its size over and over again. Let's just say, however, we do need to resize an array. Well, there are methods built in to the array class itself, one of which is called resize, which will allow you to change the number of elements in an array. However, as I've mentioned, this is an expensive operation, but it'll do it for you behind the scenes. All those copy steps, you don't have to worry about it. You just have to specify the array you wish to change plus the new size. Then you are still responsible for moving elements around to make sure they end up in the right spot. So let's take a look at how we can do this. First, I want to do one of the other neat little tricks of an array, and I will start with A2. And if you look at the values of A2, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, then 5, 5, 5. Clearly, they are not in numeric order. To fix that, all I have to do is specify array.sort and pass it the array I wish to sort as such. And as long as the elements in the array all support the iComparable interface, in other words, they have the compare_to method, then this will function correctly. How do I know int has the compare_to method? It is simple. I just simply type sum, which is an int, and look. Oh, and there it is. It has the compare_to method, but I could also take a look at its definition by hitting F12 while I'm hovered over int. It'll take me to the definition of what the int32 struct looks like, and as you can see, it is definitely iComparable. And iComparable insists that it will implement the compare to method as such. So I don't have to worry about this not working for an int. If I create my own custom data types, which is a much later conversation, then I would have to implement the compare to function myself to enable this functionality of sorting. Okay, so now I have my list in a sorted manner. I'm going to create a method here to print out my array so we can actually see it on the screen. I'll call it print array. I'll make it an int array. And again, we'll just call the parameter a. There's no reason not to. And then I will print out each of the elements. We can do it linearly up, starting in a vertical manner and then carriage return after each element, or we can go horizontally and put a comma in between each value. Well, the vertical one would be the simplest because we simply just have to loop through the array and print out each value and then make sure we do it as a console write line, which will inject the carriage return at the end. The comma one, however, is probably easier to read, but because there's going to be 4 elements initially that are printed and we have to print out 3 commas, we have to put logic in to determine where those commas are supposed to go. So I will do that just for the exercise. So I'm going to use a similar loop that I did with test method, but this time I'm going to continue the loop until I is no longer less than a.length. Then I will print out each element. I'll say console.write a at index I. Now the question is, how do I inject the comma? Well, the easiest way is to detect whether or not we're at the first index, and if we are, we do not put a comma. So we can say if I is not equal to 0, console.write comma as such. Notice here I didn't use curly braces. You could do it this way. I'm kind of one of those people that likes to see the curly braces, so even though it takes an extra few lines, I prefer it this way just because my intentions are very clear now. Then, at the end of the for loop, we still need to have a console write line to ensure that we have that carriage return at the end, so once the list is done printing, we're off to the next line so we don't corrupt the output on that same line. So let's go ahead and call print array, and we'll pass it a2. Now if I run the code, you will see it sorted 555 into its appropriate place. Okay, let's get back to the topic I was on a few minutes ago, and that was dynamically resizing an array. We could, as I mentioned, use that array resize method, and there's nothing wrong with that. It's just fewer steps for us. But sometimes it's also useful to see what the steps involved are if you wanted to do it manually. So let's start by creating a new int array called a3, and we'll set it equal to a new int array, but we have to specify a size that is one larger than our source array. Our source array, which is a2, has 4 elements. Therefore, I need to make this a 5, because remember, this value indicates number of elements, not last valid index. Then I have to issue a copy command, and the first parameter is going to be the source array, the second parameter is the destination array, and the last parameter is how many elements I wish to copy. Then finally, I'm free to add something to the last index, such as, let's say 654. Then we can print out this new array A3. Now when I run it, you will see that there is still a discrepancy. in that we're no longer sorted. I'll copy the sort method and make sure it sorts A3. And then I'll reprint the array. Now when I run it, you'll see everything in the appropriate order. Of course, I could have inserted the new element 654 into the right location, but then it would require me to do something called a binary search or a linear search to find the appropriate index to insert that element. That in itself takes some cycles because a binary search, while being quick if it's already sorted, it can add up if you have very large arrays. Sometimes the simpler approach, even though it's going to cost you a little as far as execution time, is best because it's very clear what I'm doing here. I'm adding a new element and then I'm sorting it to make sure it goes into the right place. There are other data structures that we'll talk about at a different time, such as generic lists, which take a lot of this pain out of using an array because it is a separate data type. It still uses an array, but it takes care of all of the dynamic allocation of memory for you, and techniques such as insertion, deletion, sorting are all very simple to implement using that particular data type.